Okay, welcome everyone. I hope you've enjoyed your lunch on this beautiful warm day. Just to inform you, Brazil is down 1-0, so it's important. My name is George Athanasopoulos. I'm from Monash University, and it is a really great pleasure to be chairing the keynote for this session. It is a really honor to introduce Professor Serena Ng, who is Edwin Rickert Professor of Economics at Columbia University, and is really recognized as one of the world's leading econometricians with research interests in macroeconomics, time series econometrics, forecasting, and big data. And she also has, as we all know, several seminal papers in journals such as Econometrica, AER, JASA, and the list really goes on. Serena is a fellow of the Econometric Society, fellow of the Society of Financial Econometrics, fellow of the Journal of Econometrics, and the International Association of Applied Econometrics. Really, these recognitions are outstanding for her sustained contributions to our profession. I don't know if Serena remembers, but I've just told her that, I don't know if she remembers my name, but I've pestered her a few times to get her to the ISF. I was trying to get her both to Cairns and Thessaloniki, but eventually we've got you here, which is great to see. So without any further ado, please join me in a warm welcome to Serena Ng.
Thank you for the nice introduction. I want to thank the organizers for inviting me here, and it's good to be back in Montreal. So I imagine that most of you sitting in the room do time series of some sort, so I apologize for having cross-section in the title. So what I want to analyze is a data that has features like temperature, and so a lot of economic time series has that feature. So, so let me just explain to you how I got interested in this. So as you know, temperature has been warming, and there's a lot of interest in looking at the economic effects of warming temperature. So when you look through, read through surveys in Journal of Economic Literature, et cetera, they usually report 3 types of regressions. There's one type called the Ricardian regression, that are cross-section regressions, regressing some economic variable on some, what they call climate variable, that is average of temperature data. The idea being these are long-run relations. Then there's a second type regression that are panel fixed effect regressions, and with fixed individual country and time effects, they read out the low frequency component, and they call them the short run estimates. There's a third type of regression I call long difference regression, which has really got my interest, and they are called longer term regressions. So I just wonder what are these longer term regressions? That's how I got started into this. So in this literature, the typical finding is that these long and short run estimates are usually quite similar. And they attributed it to the lack of adaptation. So what I wanted to understand are these questions. First of all, I really want to know what are these long difference regressions doing. So long difference regression essentially take all the data, they compute 2 standard moving average, and then take the difference between the 2 long differences. So essentially, if you have a big pan of data, they collapse all the information into one period, and then you just do cross-section regression. So just like the Ricardian regression, these long difference regressions are also cross-section regressions. So that raised a lot of questions in my mind. So, first of all, why do these long difference regressions give me a medium or longer term effect? And I guess I was also very curious that precisely the long difference transformation is what I understood or was taught to be the Kuznets transformation, which was a no-no. What Kuznets did was he took a long difference of 2 standard moving average, and he generated white noise. From a white noise, he generated a 20-year cycle. I said, no, you shouldn't be doing that. So I started thinking, well, could that be the reason why these long run estimates, they all look similar? Is there some statistical explanation for this? So digging into this a little bit more carefully, I started playing around with this, and so I realized that these cross-section regressions, what they really do is they remove the time dimension, and initially I used the word timeless regression, and I read, no, this is not a good word. Time compressed seems pretty cool. So that's when I mean time compression, what I'm really saying is that I have a panel of data, I get rid of all the time information collapses into just one unit. It becomes timeless. So this is the type of data I want to analyze. I want to learn about their properties, and I want to understand whether the fact that I'm transforming unit root type data, or I1 data, or stationary data, whether the data type matters. So more fundamentally, I want to know, do the time series properties affect cross-section regression? I always thought if I do a cross-section regression, I get root n consistent estimates, and that's it. So in this analysis, what I will analyze is I'm going to consider time-compressed data of the form. I get xit, little xit. My w of t is this time-compressed function, and it will have features that I will explain later. And my time-compressed variable is x tilde ik. So what I'm going to do is I'm going to do regressions on my time-compressed y and time-compressed x. And so I'm going to have several results. First, I'm going to show that my x tilde, my time-compressed x, if it was I1, it fans out. The cross-section variance fans out. There's some words I'm going to be using over and over again in the next hour. One is fanning out. So the cross-section variance fans out. The second result I'm going to get is that if I do time-compressed regressions and the data are originally I1, I actually get super consistent estimates, meaning that they're going to converge much faster than rate root n. In fact, the fastest rate I can get is actually root n times t. Okay? And I don't have to do any hack estimation, no serial correlation, because I'm doing cross-section regression. All my estimates are consistent asymptotically normal. I can just go back to my standard normal inference. So of course, this is the textbook analysis. I get this cool result. There are empirical issues I'm going to have to discuss. And one important component of it is what was discussed in Mark's presentation this morning about the difficulty in separating out the permanent and transitory component. So there's still a lot of time series analysis involved. So I'm going to be looking at two applications. One is the effect of GDP or GDP growth on due to temperature, and the other one is the effect of inflation on demographic changes. There's some recent discussion that because the dependency rate has gotten higher, meaning that fewer people working, it might affect trend inflation. So I'm really looking at low frequency, long run relationships between variables in a cross-section analysis. Okay? So my main conclusion is going to be that time series properties matter a lot for cross-section regressions. Okay? So I'm going to start with, I'm going to start with the assumption that the data I1. This is, the top graph gives you US temperature data. The black line is the actual data starting from 1900. And the blue line is the non-stationary component estimated from the local level model that Mark explained this morning. That's going to save me explaining. The second one is the temperature series for New York. It's estimated from the black line is the actual data. The blue line is the fitted trend component from the factor model. So this is the common component in the 50 states. Okay? So it turns out that for both series, both the local level model and the factor model, both have a reduced form of that the change in temperature is an MA1 with a negative moving average coefficient of close to minus 0.8. Okay? So that's going to come back. And so a lot of these analyses, people recognize that there's non-stationarity in temperature. If it was stationary, then we shouldn't be talking about warming trends. So the fact that we talk about warming trends, we must be thinking about non-stationarity. But in cross-section analysis, this aspect is not taken into account. Okay, so what's my starting point? My point of departure is an analysis, macroeconomic analysis from Deaton and Paxson. Deaton and Paxson's analysis starts with the proposition that if consumption is a random walk, so permanent income hypothesis holds, then you take a cohort of the same age and you track them over time, income inequality will increase. Because when everyone's income is a random walk, over time, they are going to have shocks. The shocks are going to have more dispersion. Okay, so the cross-section dispersion is going to increase over time, and that's what I mean by fanning out. Okay, so it goes like this. Okay, so in Angus' analysis, this is he takes a starting point, quadratic preferences, that is a macroeconomic analysis, and he points out some economic conditions under which this fanning out effect might not hold. I want to analyze it from a more general econometric perspective. So I'm going to generalize this result from a random walk to just a unit root process with a serially correlated noise. Okay? If I do this, I'm going to get my X is the non-stationary series. I can break it up into an initial condition plus a mu IT component that is unit rooty, is non-stationary, and a W component that is stationary. So the main difference with the Deaton setup is that Deaton doesn't have the WIT because his C star of L is 0. Okay? So if I look at, simply take the cross-section variance of XIT, I immediately get that because each XIT has accumulated some of these U's. They are the shocks, right? So if I look at the cross-section, this component, the variance of this component is going to increase with little t. And that's what I mean by fanning out. So I call this a generalized fanning out. Generalized because now the fanning out is not simply proportional to sigma square I, but it also involves this term that determines the long-run variance. So it's actually t times the long-run variance. Okay? But it is still the case that even in this generalized setting, when X is a unit root process, the cross-section variance is going to fan out at rate t. Okay? In contrast, if X is stationary, C of 1 is 0, there's no fanning out. Okay? So of course, like, it is possible that this term, this long-run variance, can dampen the effect of this fanning out. An example being that if the change in X is actually a moving average component, has a moving average component, then this is my C of 1 square, and if this theta I is negative, I can completely destroy my fanning out. So part of the problem we're going to encounter later on is precisely that the fanning out will be weakened if on average this component is negative. Okay? Now, so I'm going to start looking at my time-compressed data. Okay, so what I mean by time-compressed data is that I'm going to take my X, okay, I'm just going to separately analyze it for I1 and I0. Okay, so, but now I just call it X. I'm going to sum it from T0 plus 1 to T. Okay? And WT is my weighting function, time-compressed function. I'm going to want my time-compressed function to satisfy some conditions. 1 and 2 is essentially make sure that there is a probability density. The weights are positive, they sum to 1. And the last condition makes sure that I have some weight somewhere between T0 and T1 that is non-zero, so that my WT cannot simply be a 1 in period 1. Okay? If it is too early, I don't have enough fanning out because there's only one observation. Okay? So now, paradoxically, this class of functions I analyze actually does not include the long difference, which I started the project. Okay? I will explain later why. Okay? So let me just start with the simplest scheme, which is also the result that the Deaton-Paxson reported, which is what I call point sampling. If I have a T by N panel, okay, I can take any row for analysis, for cross-section analysis, and that's a type of time compression. Essentially, I have T rows, I only take one row for analysis, I remove the entire dimension if I do cross-section analysis. Okay, so if I cannot take T equals to 1, right? T1 equals to 1, because if I did, as I said earlier, I would be just taking the first row, and there's no fanning out, because I need accumulation of the U's in order to get fanning out. Okay? If I was to maximize cross-section variability, which row should I take? I should take the last row, okay? Because that's where my accumulation of the errors is maximized. Okay? So if I was to do cross-section analysis and I just want a lot of cross-section variability, take the last row. Okay? Now, there's also a distinctive feature in the cross-section variance of this type of fanning, of this point sampling fanning out. If it is I1, it fans out at T, because that was just a Deaton-Paxson result. If it is I0, the variance is constant. Okay? So there's a distinction between the cross-section variance when it's I1 and I0. Okay? That's not the only type of fanning out we can do. So this is a lot of equations. So let me just explain to you what's going on. Well, if I take just one row, that's wasting a lot of information, right? So why don't we do average? average seems like a good thing. So, so I'm going to define my K average to be summing from T0 plus 1 to T. So what I mean by K is simply T1 minus T0. Okay? Now, if I carefully work out everything, so the 1 over K is the WT. Okay? This is the weight applied to X. Okay? But what really matters for fanning out is not the WT applied to X, it's actually the weights applied to the U's. Those are the innovations to the X. Okay? So if I do this, I find that the weights that I call phi j is like this. It's actually a triangular form. Okay? So this, so how do I analyze this? Well, so it turns out that if K is equal to T, that means I take full sample average. I don't need to do a whole lot of math. I already know the answer. I know that if I'm doing averaging, okay, if the series is stationary, then variance goes to 0 at rate T. Okay? If it is I1, I know from functional central limit theorem what the convergence is, and I know the variance of this term, and I know it's 1/3. Okay? So I know then that the variance of time compression by K averaging is going to fan out at rate T, but now it shrinks to 1/3. Okay? So compared to point sampling, when the fanning out was full, I get full fanning out. If I do averaging, I thought I was using more information. I actually lost 2/3 of the fanning out. Okay? So what happens here is precisely because of this. Okay? While I'm summing up T observations in terms of the innovations, I'm actually giving triangular weights to the innovations. So a lot of innovations actually get less than unit weight. And that's, as a consequence, my weights shrink to 1/3. Okay? So working this out, working this finite sample analysis is useful because if I do this asymptotics, as in applying functional central limit theorem, I do not recognize that there's an initial condition involved. I do not recognize that this initial condition can also play a role. And in fact, this 1/3 just comes from taking the limit of this sum. Okay? So, but it is nonetheless true that if K is large, my fanning out, the rate is K, it is proportional to the long run variance, and it shrinks by 1/3. Okay? So here another contrast, right? So with the point sampling, I get, if it is stationary, the cross-section variance is O1. If it is I1, it's OK, order K, not OK. So if it is K averaging, if it is stationary, it's order K minus 1 over K. If it is I1, it blows up at 8K. So different fanning out schemes have different implications. Now, long differencing. This long differencing does not belong to the class I started the exercise with, but I have to analyze it because I started off with this exercise. It turns out it's really hard to analyze this thing, so I thought the easiest way is actually to write down exactly what it is doing. So what it is doing is it takes two centered moving average. Okay, centered moving average is computed when it is centered at T1. It takes takes the mean of T1 minus m to T1 plus m. The little m is the number of periods you want to do the centered moving average, and then you take the difference between the two. Okay? So the tuning parameters in this exercise, you have to choose T1, T0, and you have to choose the little m. Okay? Now, if you write out, I decided I'm better looking at this through an example. So the W2 is the weight on the x, and the phis are the weights on the u's. Okay? So what you see is that why does it not fit into my class of functions I want to analyze? Because some of these w's are negative. I want my w's to be all positive. And these w's don't sum to 1. Okay? I need my w to sum to 1 to be a probability distribution. So I can analyze the next step, LD, in the next step using the framework I will develop. However, this string of ones on the u's is actually very useful, because now it gives unit weights on a lot of observations. Okay? So as a consequence, it actually fans out at rate K. It's better than averaging. Okay? However, you have to choose an M too. So the bigger M you choose, the more observations you use in centered average. Even though M is fixed, you're going to lose the fanning out a lot. Okay? So the rate you should get is roughly K minus M over 3, and if M is big, it can be slower than point sampling. Okay? So this is describing to you what the LD does, but conceptually, what exactly is the LD doing, right? So LD, So you'll see that because it's differencing, there's no initial condition involved. Okay, so which is great if you have fixed effect, it difference it out. If you have additive fixed effect, it difference it out. Now, so since it involves averaging and differencing, so in a time series sense, it is going through a low-pass filter, which is the averaging part, and a high-pass filter. Okay, and I can work that out that roughly it is screening out, is keeping variations with periodicity roughly 2mk over m plus k. Okay. So in this literature, in this climate literature, this is how I got really confused about how to think about these. People choose m and k, and this is not meant to be criticism. It's, so m and k, they choose these parameters. According to my formula, the implied periodicity is 15. They call this a medium-term effect. Some other paper has an implied periodicity of 8, and then they call this a longer term. Okay? And I think more confusing to me was why are these called longer term effects? They are, even if you isolate variations of particular frequency, you're characterizing the relationship at that frequency. You're not analyzing a medium-term effect. So very confusing. So I have something more to say later. So now, this was exactly the Kuznets filter. So how did they get by not having a spurious regression? And I finally understood that, well, that's because the LD transform is they take data at the two averages constructed centered around T0, T1. They do it for every series, and they never use the time series variation. They use the cross-section variation for regression. So there never was a spurious regression problem, because all they use is the cross-section variation. And for that matter, the same can be said about K-averaging. K-averaging is a low-pass filter. If it used time series regression in average data, we would also have spurious effects. But since we're doing cross-section regressions, I will be doing cross-section regression, I'm spared from that critique. So let me just show you some simulations. The top one is generated from the local level model. The lower one from the factor model. I choose parameters such that my implied moving average parameter ranges from 0 to -1. If it is -1, there's no more fanning out. If it is close to 0, I have maximum fanning out. And this is point sampled. So my T0 is 10, 20, and 50. So indeed, the cross-section variance at T1 is almost twice the one at T0. At T, which is 5 times T0, is roughly 5 times. And if it is K-averaging, this one is about 1/3 of what I do with point sampling. And you see, with long differencing, you get very good fanning out if m was 0. But then once you let m get bigger, you lose the fanning out. So the transformation scheme matters even when you do cross-section regression. In that sense, it's no different from doing time series regression. Now, if my theta, unfortunately, is very close to -1, you see that I lose all my fanning out. Okay, so this is temperature data for 48 states. Okay, this is the time series pattern. This is now I show it only from 1980 to 2020 because my GDP or GSP data, General Gross State Product data, only starts from number 1960. Something, so I can only start this analysis from 1960, and this is the cross-section variance over the same horizon. Okay, so is it fanning out? Is it no? So I think it is fanning out to some extent. Okay, so now different series to look at. Dependency ratio. So this is the fraction of the younger than 15 plus older than 64 as of in the total population. This is the data, okay? They don't look very stationary to me, but look, they actually don't fan out, they fan in, even though this looks non-stationary. Okay, so there's something to be understood here too, so we're going to get to that a little bit later, okay? So now, having given you 2 examples, one for point sample data and one for K-average data, I can give you some generic properties of this time compressed data, now generically written in terms of the W's. Okay? To cut a long story short, I know this is a lot of equations and it's after lunch. So for I1 data, I can write my time compressed data as a function of the initial condition and weights on these shocks. It's the weights on the shocks, the phase that is important. Whether the phase is just the sum of the weights. Okay? I can show that the variance of the time-compressed data is initial condition, variance in initial condition, plus a variance times this term, and this phi of k is some parameter ak times k, and this is where the fanning out in, and this a tilde k is going to depend on w. So for k averaging, it is 1/3, for point sampling is 1, and you can design all the different schemes. One that I skipped through when I showed you the simulations was a scheme in which it was 0 for the first half of the sample, but 1/k for the next half of the sample. That still works. Okay? So this is it for I1 data. I basically get a phi k that is proportional to k with a proportionality factor that depends on my choice of the weighting function. I do the same exercise for I0 data. Now I'm again writing my time-compressed data as a function of the u's, with a weighting function that's now called phi instead of psi instead of phi. And this psi function is a function of the w, but now it depends on the AR1 parameter rho. Okay? And after some work, you can show that the variance of the time-compressed data is this GW times sigma square over 1 minus rho square, which is just the unconditional variance of the AR1 process. So collectively, I can write this as sigma square I times psi of k compared to the I1 case when it is sigma square I times phi of k. Okay? Now, I have this A here, and this A is the weight applied to rho to the h, the lag h weight. So what's significant about this result is that because the GW is the mean of rho I to the h, and rho is between 0 and 1, my GW must be bounded. Okay? So why am I doing this? Because now if I know that the phi of k, which is for the I1 case, diverges with k, and I know that the phi, the psi of k for the I0 case is bounded, how do I go from the unbounded case to the bounded case? Okay? Precisely what happens when rho is close to 1? That's what I want to know. Okay? So why is this interesting to know? Because in time series, in unit root analysis, we know there's a discontinuity in the properties of the AR1 process as it approaches the unit circle. Okay? So it turns out that in this setup, okay, because GW is bounded, if the variance of my time-compressed variable was to diverge, it cannot come from GW. It has to come from this term. It has to come from sigma square over 1 minus rho square. Okay? And in the local to unity framework, I can show that indeed in the local to unity framework, this term blows up with k. Okay? And more generally, if instead of the local to unity framework, I have C of I over k to the d for some d that depends on how persistent the process is, this variance is going to gradually blow up as d moves towards 1. So the long story, the short version of this long story, tedious analysis is that there's a smooth transition of the variance going from the I0 case, which is not very stationary, to increasingly persistent to the very persistent case of I1. And because of this smooth transition, what I will get later on is that when I do regression, there is a smooth transition in the convergence rate as I regress variables of y of the time-compressed y on the time-compressed x without ever knowing where the process is I1 or I0. And this is what I'm going to do next. Okay? Okay, so I'm going to get to the... okay, so what have we been doing when we analyze highly persistent data? Well, if we do time series or panel regressions, for those of us who spend quite a bit of time in a career worrying about it, it is always the case that, well, we get super consistency, but the distribution is often not asymptotically normal, so we spend our time doing all sorts of stuff to be able to do inference. Okay? If we analyze the low frequency component, as in Mueller-Watson, we ended up with a small sample problem. So I'm going to try something different. Okay? So of course, I have to have enough ends. I have to have enough cross-section units for me to be able to do this. So instead of doing a time series regression, I'm going to take the time series data. I'm going to compress everything so that there's no more time dimension. I'm going to do cross-section regression. Okay? So my DGP looks like this. Okay? So This is the unit root process. I have my U's. I will simply assume that there's no serial correlation just to keep things simple for now. And my regression is just, this is a DGP in a regression. I'm going to add a constant term in, okay? Now, instead of going through the math, let me just give you roughly the idea of why I get super consistency, okay? Supposing I have very well-behaved properties. My X is orthogonal to E, so that the numerator is going to have a limit of 0, okay? The denominator is simply the variance, the cross-section variance of X, okay? So whether I have I1 or I0 data under these ideal conditions, I should at least get root n consistent estimates. Okay? So, so this framework also works for I0 data. But what's happening here is that because my data are possibly I1, and if it's I1, the denominator is going to be of order k. So if the denominator is of the k, it's going to go to 0 very fast. And this is what I call signal magnification. Okay, so this is our standard x prime x inverse, the limit of x prime x inverse. The denominator, okay, it has a central limit theorem, and it has a variance. Okay? Now, if nothing else happened, I would have my root n consistent estimates. But what if the error term here, the e to the ik itself, enjoys noise dilution? Okay? For example, if I'm averaging a stationary variable, this stationary variable is going to have variance that goes to 0 very fast. So if I get both effects happening, both the denominator exploding very fast and the numerator going to 0 very fast, I'm going to get very, very fast convergence. Okay? If I only get the denominator to diverge very fast and the numerator does not gain from signal noise dilution, I still get faster than root n convergence, and that's essentially is how I get my result. Okay, so the next few slides is just basically going to say that if I do k averaging, whether I do k averaging or point sampling, I know the denominator from fanning out is going to diverge with k. So I know at the minimum I'm going to get root n times k convergence. Okay. However, if I do k averaging, this noise itself goes to 0 at rate k. Okay, so I'm going to get super fast convergence, and I will end up getting root n times k. If I do full sample averaging, my fastest rate I can get is root n times t, and that's super, super fast. Okay, so in some sense, I get back all the nice results from the super consistency results from doing time series regression, but I'm doing it in a cross-section sense. Okay. Okay, so this just formalizes for you the conditions under which I get signal magnification and noise dilution. Okay. Okay, so and this is really just saying what I just said intuitively just now, and I hope I convince you to some extent. I can actually do better, because if I was doing time series regression, I know that if I have a deterministic trend, I can get faster than t convergence. I can get t to the 3/2. The same happened here. If I have a random walk with a drift of GI, I get even faster rate convergence. All those results are preserved because my data is now fanning out so fast. My signal magnification is really, really fast. I have also assumed that initial condition is 0, but if the initial condition is not 0, but the process started way, way, way back when, okay, then my actual divergence is actually a lot faster than T0. Okay, so there are many ways I can even speed up the rate, but I was happy to just assume, x0 is 0. So here is another intuitive way to explain to you what's going on. Okay, so I can write for you a sandwich variance form, which is kind of complicated. If I strip everything down to homoscedasticity, I really just need sigma square QXX inverse in Bruce Hansen's book notation. Okay, so this is sigma square QXX inverse. Okay, so what's going on? Well, the QXX part is sigma square phi k. So it's this guy. That's a sigma square QXX inverse. The numerator, the noise dilution part is this part. The tau and the sigma square we can't do anything with because that's data. What we can do is to choose W. Okay? I know my phi k is A tilde times K, and A tilde depends on my choice of W. Okay? The denominator likewise depends on my choice of W. So depending on how I choose my W and I either end up with root nk convergence or root nt1 convergence, but both are super consistent asymptotically normal. Okay? So I'll skip this because, no, I should not skip this. So I have analyzed this under extremely ideal assumptions that, I've strict exogenated everything. What if my true model is actually a dynamic model? I estimate a static model, and that's misspecified. Okay? So it turns out that what I omitted is a stationary component. Okay? And the stationary component is dominated by this I1 component. So even though if you think in terms of bias terms, there is the covariance between x and the error term. Okay? So now that covariance term is not zero. I have a non-zero covariance because of omitted variables, but the denominator, the x prime x part, diverges so fast that any misspecification, so long as of O1, is not going to affect my consistency. It only has an efficiency implication. So this same result is going to go through not just for estimating a static model when my true DGP is dynamic, but also if I relax the strict exogeneity assumption. I still get my super consistency. So when may I lose super consistency? Okay, so not everything is always so super duper. And that's when I have heterogeneous coefficients. If I have heterogeneous coefficients, my beta I is beta plus some noise. Okay, so my regression now has an error term E star that includes this variation from the beta multiplied into x. Okay, now this is bad because every time my variance in x scales up, I also scale up the variance of the E star. Okay, so I have signal magnification, no problem. But as I magnify the signal, when I have heterogeneous coefficients, I also magnify the noise variance. Okay, so I don't gain anything. Not gaining anything means that I resort back to my original root n consistent. So the nice thing about this is that you don't need to know whether you have I1, I0, because at the end of the day, you still can use standard normal inference. So this is just to simulation to show you what's going on. So here the true parameter is -1, okay? So here's the true parameter value, okay? So if I do point sampling, k-averaging, or long differencing, these cross-section regressions are precise, like really, really precise, okay? Now, how about if I use it for hypothesis testing? The distribution should be standard normal. So if I test the hypothesis that beta goes to -1, so this is the size of the test. Okay, they're all, considering that this is size of 50 and 50 for T and N, this is pretty good. Now, if I want to take an alternative at 0.97, if I do k-averaging, this is the power I get. If I do full sample averaging, if I do subsample averaging, I lose a lot of information. Now, what if I do long differencing? If I do long differencing, like comparing this, right, so I have to do T2, I should compare T2 with this, okay? Instead of getting some power like 0.82, I'm getting 0.318, okay? That's because my divergence rate of my long difference averaging is K minus M, okay? So when my little m is 4, my big M is 2 times M plus 1 is 9. So I lose out a lot. The long differencing is not fanning out as much, okay? So it is behaving as though I was doing point sampling, okay? So the point here is that the time compression scheme in general will give us super consistent and asymptotically normal estimates, but how we do the time transformation, time compression actually does matter. Okay? So let me spend the rest of my time on empirical issues, okay? So I'm going to go back to these regressions, okay? So I was kind of explaining to you what is a Ricardian regression. So in my time compression scheme, I need a time compressed variable on the left-hand side, I need a time compressed variable on the right-hand side. Okay? The right-hand side the WMO, this is a World Meteorological Association, usually takes 30 years to be a long-run average. So they do 30-year average, and that's okay. That's like my time with K goes to 30. The left-hand side is more dubious, what they're doing, because what they regress, the left-hand side variable is actually the present value of land. So it is some kind of discounted average, but a theoretical concept, not a statistical average. So it's kind of a K-average regression, time-compressed regression, but not quite close enough. Okay, now the main drawback or highly criticized aspect of these so-called Ricardian regression is that if you do a cross-section regression, you might omit a lot of fixed effects. Okay, I'm going to come back to this. If we do panel regression, then I understand why they do panel regression. It's interpreted as short-run effects, okay, because if you put a fixed effect, a trend on as fixed effect, you basically remove all the high-frequency variation. You end up estimating short-run effects. And then they say that the LD estimates long-run effects, and these results suggest nonlinearity being important, and long-run and short-run estimates are similar and suggest no adaptation. So I want to go through each of these issues from the perspective of time-compressed data. Start with the simplest, which is nonlinearity. So follow this paper. This is the DGP with a quadratic term, which is nonlinearity. Now, if x was I1, x squared is neither I1 nor I2 because differencing it does not make it stationary, so it's not I2. So inference, if you simply do a regression with x squared, when x is I1, is a mess. Okay? So what the Burke and Emmerich does, they do, I think something is not quite right. They construct this variable, that is the average, and then they square the average. Okay? What I think they should be doing is they take the square and then they time compress the variable. So in our case, because if x was I1, x squared is still going to fan out. The time compressed square is still going to fan out. So I would have no problem analyzing the nonlinearity in a cross-section regression, and I would still get consistent, super consistent asymptotically normal estimates. Oops. Now, fixed effect is probably the most criticized aspect of it. And the idea goes like this. Okay, so if we have an omitted fixed effect, okay, this is the analysis I do. So I would get a bias that whittle down to the mean of ft times the covariance between xi0 and the S0. Where did I SIT0 from? Because I rewrite xit to be the initial condition plus all the cumulative U, and the U's are by assumption uncorrelated with S, so I ended up with the xit0. Okay, so my claim here is that if we average the data, now I'm making statements more specific to K averaging, omitted time effects is an efficiency issue, it's not a bias issue. Why? Because if this term is 0, I have no bias. So it remains root NT super consistent asymptotically normal. If xi0 is 0 and this covariance term is 0, I am root NT consistent because this S0 is omitted, so it inflates noise. It has cross-section variance, so it's a bigger variance. Now, if x is correlated with this initial condition, I still have many ways to fix this problem. Okay, I can control for it. If I have some observable zi, do like a control function approach, I can reduce this bias that is of order k minus 1. Why is it of order k minus 1? Again, it is because even though the covariance is not 0, the denominator, which is the signal magnification, goes to 0 with k so fast that any bias goes away. Okay? So I also have other ways to get rid of it, such that making the assumption that the initial condition is not 0, or I have a drift. Okay? So in my simulations, I actually have to work pretty hard to find a case when, I'll show you what this is, okay? So now my estimates have different rates of convergence. The top one is just beta hat minus beta. You probably can't see what is written here, but the blue line is a point sampling estimator, and I'm multiplying it by root n times t. The red line is the k averaging. I'm multiplying root n times the t outside. So that this red line is converging faster than the blue line, But once I multiply it by the appropriate factor, the scale is roughly right. So I think it's true that the K-averaging one is converging faster. And then when you standardize everything, the t-statistic looks looks pretty normal. So I feel pretty confident we can do standard normal inference under these standard conditions. Now, when is the condition going to be not so happy? I'm not going to go back to the problem that Mark talked about. So Mark talked about the possibility that inflation has two components, a permanent component and a transitory component. I'm going to assume that it has a permanent component, which I think of as warming trend, and I have a W component, which I think of as heat waves. I can have both types of warming features to coexist. I don't have to have one or the other. Okay, so I'm going to end up having a I1 component plus an I0 component. And in fact, the two pictures that I showed you earlier, one from the local level model, one from the vector model, both has this type of feature. Okay? So what is the consequence of this? Well, both have the IMA1 as reduced form with the parameter that depends on the signal-to-noise ratio. Okay? In the local level model, okay, it is, as Mark said this morning, is the ratio of the permanent to the transitory variance. In the case of the vector model, it depends strongly on the variance of the vector loadings. Okay? Why? Because the vectors are common. So the only reason to give you cross-section dispersion or the fanning out is the lambda, is the vector loading. If the lambdas are homogeneous, you don't get any fanning out. Okay? So if I have no fanning out, okay, if this signal-to-noise ratio is close to 0, I will still get back root n convergence. It's not like I get inconsistent estimates. I just don't get fanning out. Okay? So why I thought this might be a reason why the short-run and long-run estimates might be similar. Okay? So this, think about this regression in time-compressed data. Okay? If my coefficients on the I1 component and the I0 component are identical, beta mu equals to beta W, no problem. Okay? But they may not be identical, and if they may not be identical, then we're in a situation like Friedman's testing permanent income hypothesis. You regress consumption on actual income, you're going to have the weighted average of the two, and that's what I'm getting. Okay? So how does K-averaging the low-pass filter going to help? Because the averaging is going to, the variance of the I1 part is going to blow up with K, and this part goes to 0 at K. Okay? So what happens is that my choice of K, my choice of K helps me isolate the permanent component without ever specifying the model for the permanent component. So in this example, my true coefficient for the permanent component is -1. I have a transitive component with a coefficient of -0.25. If I make K small, my estimate is closer to the transitory component than the permanent component. I need a very big K in order to get the right estimate. Okay, and this is what this is showing. So if all goes well, if my K is chosen, I can look at this graph and see what type of K I need in order for the beta parameter to stabilize. If it is not stabilizing, that means my K is not large enough. This is the empirical exercise I kind of learned from it. However, the K here is used to isolate the variations in the permanent component. It is not used to isolate a horizon-specific effect, which is how I think the literature seems to be interpreting it. I think that's not quite right. So this really, this is just a simulation reflecting the figure I showed you earlier. Okay? If my signal-to-noise ratio is high, I very precisely estimate the -1, which is the true coefficient on the I1 component. Okay? If and the standard errors are small, and the K-averaging has much smaller standard errors than the long differencing. If I have a small signal-to-noise ratio, it gets increasingly contaminated by the I0 component, and I cannot distinguish the two. Okay? So the empirical question then is, this is the data I look at. This is the fanning out. Are we fanning out enough to give me a precise estimate? That really is the empirical question. Okay, I have a moving average component is minus 0.8. Is it fanning out enough? Okay, so there's also a debate in the literature: is temperature affecting growth rate or level? So I do it on both. Okay, so the top one gives you the level, and you see that it doesn't matter what K I use, it is not stabilizing like I saw in my simulation example. It should be stabilizing if there exists a K that allows me to isolate the permanent component, but it is not. Okay? The growth rate, same thing, it's not stabilizing. So these two regressions are done without the fixed effect. Now, what if I add the latitude of the country as a fixed effect? Because remember, another critique of this climate regression, of cross-section regression, is that we omit fixed effect and it's a bias. Okay? So if I include the latitude of the country, now things stabilize, both for level and the growth rate. Okay? So I interpret this is that in the climate application, fixed effect is important, but it is also the case that the mixture of the I1 and the I0 component makes it really difficult with a finite sample. I have to have enough Ks to do the averaging to get me the right estimate. But with controlling, even controlling for fixed effect, I still need about K equals to 20 in order to isolate the effect with some confidence. Is this always the case? I'm going to look at different examples. So this is the first graph is the one I showed you earlier on the dependency ratio. The cross-section variance actually fans down. Okay, so what's going on, right? So this looks like it's I1 trending, but this is fanning down. So what happens is that the dependency ratio is the sum of the old plus the young. Unlike the temperature, when I don't observe the permanent and transitory component, I actually observe the old and the young. I have data for that. This is the share of X1 is the old, X2 is the share of the young. Okay? What you see is that the share of the old is trending up, and the cross-section variance is fanning out. The share of the young, I think it's because of decreased fertility across developing countries, is this convergence in the young ratio. So it is actually fanning down. Okay? So it is fanning in. Okay? So, however, even if it fans in, I can still do a regression. Okay? Some explanations for fanning in. Okay? But because I observe both the young and the old, I actually can do the regression on the young and old separately. Okay? So first, the top graph shows you that whether I include the control or not, and I include initial population as control, it doesn't matter in this example, not like in temperature. In temperature, when I include a control for fixed effect, the picture completely changed. In this application, it does not matter. And then when I separately regress the young on the old, I actually get significant estimates. What am I estimating? I'm regressing inflation on demographics. Okay? So there was some concern that because the old and the young are not saving enough, okay? They're not saving as much as the working age population, that drives up, they're consuming too much, that drives up inflation. So there was some concern that changes in demographics may affect the inflation rate. So in this application, I don't have to distinguish between the permanent transitory component. I just separate out the two components. My dependency ratio is still a sum of the two components, and I can pretty precisely nail down these things with estimates that are consistent in it. This one is consistent asymptotically normal because it's the old. The young looks like it's not fanning out, so this one is root n. This one is faster than root n. But from an inference point of view, I don't need to know the rate. I just need to know that it's standard normal. Yep, done. Okay, so I think that's, I throw in this last slide, implications of forecasting. I feel like I need to say something, but I don't really have a whole lot to say, except to point out that one, this talk is really about estimating beta. If you need to forecast, you cannot ignore the eta IT anymore. Eta IT is the short-term variations that from the point of view of estimating beta is irrelevant, but from the point of view of forecasting, it matters. So you may ask, well, why is it that the K-averaging cannot estimate this? I cannot estimate the eta, the parameters corresponding to eta in my framework because I run into nickel bias problem. Once I put a lag-dependent variable in, I have nickel bias in my cross-sectional regression. I can't do it. Okay? So the upshot of this is that time series properties of the data matter in cross-sectional regression. I started this project, it never crossed my mind that I should think about time series properties when I do cross-sectional regression, but it turns out that it does. I can get super consistent asymptotic normal estimates with getting rid of the time dimension of the data properly, but how you do the time compression does matter. And if I return back to my temperature data, I suspect that we do have to control for the omitted fixed effects, but it is more likely than not that there is a big problem distinguishing between a permanent and a transitory component. Okay, thank you very much.
Okay, as people are moving to next section, let's take one question just to give a chance. Does anyone have a question? There you go.
Oh, thank you very much, Serena. Very interesting. I was wondering about the possible heterogeneity in the beta. So if you've been thinking about random effect or...
Yeah, that's the heterogeneous coefficients case, that when you have heterogeneous coefficient, you will scale up the variance at the same time you scale up the x. So you gain nothing, you get root n.
Okay, let's put our hands together for Serena once again. Thank you. There is a practitioner session in here now, and the rest of the sessions are starting in 4 minutes. So, thank you. Thank you very much. You're here, right? Yeah.